Okay. So, good afternoon. We are Group 8, and for our problem, we've been given the open loop transfer function to be this, where K is the amplifier gain. So, the amplifier gain normally determines how strongly the system responds to an error signal, and T is our time constant, which represents how quickly the system dynamics respond. Okay, so we've been asked to determine by what factor the amplifier gain should be reduced so that the peak of overshoot is reduced from 75 to 25%.
My name is Eunice Searchman, and in this section, we would now find the closed loop transfer function of the unit feedback system. So we use the formula now since it's a unit feedback system, that means HF is equal to 1. We have HF. And since we already have GS in the question given, we just substitute. So Q over S plus 1 plus 50 over 1 plus Q over S plus 1 plus 50. So we'll solve the denominator first. So this, find the LCM is 1 plus S2. Then multiply S into bracket 1 plus S2 plus K. Then after solving for the denominator, we'll now put it back into our equation here. So we'll have K all over S into bracket 1 plus S2 all over. Then what we have here, that is S into bracket 1 plus 1 plus S2 plus K all over S into bracket 1 plus S2. After getting this, we'll now multiply by inverting the denominator. So we have K over S1 plus ST, and we invert this. So times S1 plus ST all over S1 plus ST plus K. And now in this case, we can cancel this and this. So we have K over S 1 plus ST plus K. And if we multiply through, our final equation would be K over S plus S squared T plus K. Now the denominator is very important because this helps to tell us the dynamic behavior and also the stability of the system. Thank you.
Hello, so I'm Ms. Lina and today I'll be deriving the characteristic equation. So to derive that equation, we are going to equate the numerator of the function here to 0 and divide it by the time constant t. So for the characteristic equation, we have f squared plus s squared t plus s plus k equal to 0. Then we do the division by t. So for that, we have divided by t divided by t divided by t. So we have s squared plus s on t plus k on t equal to 0. So this is the characteristic equation, and this helps us determine the location of system of poles, which also helps us to determine how the system will respond over time. So to analyze the response of the system, we have to compare this to the standard second order system form to get the response and to analyze the response of the system. Thank you.
All right. So I'm Stephanie. I'm going to take us through the second order system of our equation. So this is our characteristic equation, and from this we are going to introduce S to be a coefficient. So we are going to have S squared plus 1 on t s plus k on t is equal to 0. So we are going to write our second order system equation from this. So you are going to have sorry. All right. So with this equation, omega n stands for the natural frequency, which represents how oscillatory the system is, and zeta determines how oscillatory the system response is. So from this, we are going to compare the coefficients. So first of all, we are going to compare S to be our first coefficient. So you are going to have 2 zeta omega n, which is going to give us 1 on t. And from this, you are going to compare to k on t. So you are going to take the square root of both sides. You're going to have So we are going to substitute omega n into this equation, which is going to give us NT. So from here, we are going to make zeta the subject. So zeta is going to give us 1 on 3. This is our final answer. Hence, the damping ratio depends on the K, which is our gain. So as the gain increases, the damping ratio becomes smaller, which means the system becomes more oscillatory and produces a larger overshoot. Thank you.
Okay, so my name is Gerald, and I'll talk about the peak overshoot. Now, the peak overshoot in control systems refers to how much an output exceeds a set final value in a transient response. And so, for a second order system, the expression for a peak overshoot is m of p is equal to exponential of I over square root of 1 minus where zeta represents the damping ratio. Now, what can we deduce from this? We can see that the peak overshoot of a control system is solely dependent on the damping ratio and no other parameter. Thank you.
Okay, so my name is Fred Bile, and I'll be representing on how to apply the overshoot formula to the two cases given in the question. So first, we have the overshoot formula on the board, and then we were given the first case to be 75%. So let's represent the first overshoot with a 75%, which is going to give us 0.75. And let's represent the second case, which is 25%, to be 0.25. So we substitute the first case, both the first case and the second case, into the overshoot formula, which is going to give us 0.75 is equal to e to the power minus pi. So then this is for the first case. So for the second case, so let's make this equation 1. And for the second case, we have 0.25, which is equal to e to the power pi with the square root there, 1 minus. So let's call this equation 2. So then we take natural log of both sides for both equations. So for equation 1 becomes ln of 0.75 is equal to the ln of e to the power minus pi 1 minus the damping ratio squared. So this is equation 1, and for the second equation, natural log of 0.25, which is equal to the natural log of e to the power, a fraction with numerator pi, multiplying the damping ratio for the second case, the square root of 1 minus the damping ratio for the second case. So taking natural log of 0.75 gives us minus 0.287. So we have minus 0.287 equals minus pi, the damping ratio for the first case, and the square root of 1 minus the damping ratio squared. So this for equation 1. And taking the natural log of 0.25 gives us minus 1.386, which is going to be minus 1.386 equals minus pi, the damping ratio for the second case, all over the square root 1 minus the damping ratio for the second case squared. So this is for equation 2. So the negative cancels the negative. The negative here cancels this negative here. So we have 0.287 equals the pi all over the square root of 1 minus. So this is for the first one. We have 1.386 pi all over the square root of 1 minus. So this shows that the value of the damping ratio for the second one. So this shows that the value for the damping ratio for the second case is much larger than the damping ratio of the first case. And this is because of the 25%. So this means the 25% is lower than the 75%. That's why we have a larger ratio than the first one. So that means having the 25% is lower than the 75%. So the 25% gives us 1.38, which is larger than 0.287.
Okay, I'll be talking about linking the damping ratio. Something like this. So to the gain in the system gain. Okay, so let the original gain be K1 and the reduced gain be K2. So for the damping ratio for the original gain will be 1/2 K1 for this, and the damping ratio for the reduced gain will be 1/2 K2 T. So you divide this one by this. So this will be 1/this K2T all over 1/K1T. Oh, these two will cancel this one will cancel this one. We'll be left with, this implies that the damping for the reduced will be, and this one will come upside down. It will change this, so it will be like this. Okay. As then you multiply this one by this one, so you get be like this. As this one is directly proportional to this, when this one increases, this one when this one decreases, this one will increase. When this one increases, this one too will decrease. Thank you.
Okay, so after solving the equation, we had K1 to be equal to 20 K2.
This means that the original gain must be 20 times larger than the new gain, and that will mean that the amplifier gain must be reduced by a factor of 20 in order for the overshoot time, so that the overshoot time can be reduced from 75 to 25%.
So physically, reducing the gain increases the damping ratio, which makes the system less oscillatory and more stable. Thank you.